We're going to talk about intensity now. When it comes to waves, and we want to talk about how that energy of the wave essentially spreads itself over a certain area, we're talking about intensity. That wordage is probably not the best, but intensity, I, is the power generally of the source that's emitting the wave. So power of the wave itself divided by the area that the wave spreads over. And so this area, there's not one set equation for this. If the wave is emitted in all directions, so if the wave is emitted in all directions equally, then this area is the area of a sphere. So 4 pi r squared. This would be true for, we can assume it to be true for, say, a light bulb. If we have a lamp, we have this light bulb, we know light is being emitted in all directions. It's coming out at us, going away. Now, of course, a bit of it is being blocked by the base of the light bulb, but that little bit of an area is fairly insignificant compared to the area that the light does go. So when I'm dealing with this light bulb, it doesn't matter if I'm in this direction, some distance r, or this direction, some distance r, or this direction, some distance r. That intensity, the light reaches that distance. And so the intensity is the same from my observation as long as I'm the same distance from that light bulb. And so we consider a light bulb as a type of wave that is emitted in all directions equally. Another example would be a speaker, sound speaker. So if we're at a concert, the sound is going to be emitted in all directions. It's not perfectly equal in all directions, but we will go ahead and assume it to be, just for our intents and purposes right now. But if I'm, say, at a concert, I don't have to be directly in front of the speaker to hear it. I could be to the side, I could be behind it. Now, granted, some locations will be better than others, but we're going to go ahead and assume a speaker emitting sound is also a type of wave that is emitted in all directions equally. And so the area in our intensity equation would be the surface area of a sphere. And that just means if I'm the same distance from the source, I'm going to observe the same intensity. With light, the intensity is directly relating to the brightness that we see of the light. So a bigger intensity means that light bulb appears brighter to us. For sound, is loudness a word? Sound intensity is going to be related to how loud that sound is for us. Now, the other way a wave can be transmitted is it could technically be concentrated in a beam of sorts. So, for example, a laser pointer. The light comes out of the laser pointer as a beam. If it shines on something, we just see a tiny little circle. And so if we were to use this equation for intensity, we would want simply the area of this little circle that the light makes on whatever we're shining it on. So it's a much smaller area, which is why laser pointers can look more intense than, say, a light bulb with a similar power. Sound could, in some ways, be emitted along a beam or concentrated of sorts. A megaphone. If you go to a football game or basketball game, sometimes the cheerleaders have megaphones and they speak through this end and it focuses the sound more coming out this end. And then that by concentrating that sound, they can be heard farther away. So as we solve problems, and if there is any problem we're looking at that's not a light bulb or a speaker, where we're going to assume the situation down here where they are emitting equally in all directions, then the problem will need to have something about it that leads us to know if the sound or light is emitted in all directions equally or if it's concentrated somehow in a beam. Now, power, I don't know if you happen to remember, power is energy per time. So technically we're talking about changing energy from one form to another. So for example, a speaker is driven by some sort of oscillator that causes the speaker diaphragm to vibrate, which in turn causes vibration of the air molecules immediately next to it, which in turn vibrate the air molecules next to them, and then their neighbors and their neighbors and their neighbors. So it's creating the sound wave. So when we talk about the energy per time, we're just saying how fast this oscillation energy, which ultimately is driven by typically some sort of electrical source, how fast that is driven, changed to the form. Whether that form is sound or light, we're talking about just the rate at which that energy is changed per time. If you remember, our SI units for energy are joules. Time is seconds. So we can also call this a watt. And so the units of power we will see as just W for watts. So units for intensity will be watts per, area, regardless of which situation we're talking about, the area ends up being in terms of a meter squared. So the units of intensity are watts per meter squared. And again, intensity is relating back to brightness if we're talking light, or how loud the sound is if we're talking sound. Intensity of a wave at an ocean wave, for example. We could talk about the intensity there. So intensity is not unique to sound or light. Those are just typically the situations we're more familiar with it in. Excuse me. Now, one other situation here is with sound, we talk about what's called a sound intensity level. This one word means we're not talking watts per meter squared. It means we're going to talk decibels. We'll see that abbreviated as a lowercase d and a capital B. It turns out sound intensity levels span a huge range of numbers. So for example, the softest, the absolute smallest, softest intensity normal hearing could hear. We call this value the threshold of hearing. We use an I naught to represent it. It has a value of 10 to the negative 12 watts per meter squared. It's an extremely small number. Not everyone can hear this small of an intensity, but on average, this is about where it is. It also is going to depend upon the frequency you're listening to. Our hearing changes with time based on what we've subjected ourselves to, and we tend to lose different frequencies, our ability to hear those very well. Now that's the absolute quietest, but if we are subjected to, say, a concert, and of course that's also going to depend on, well, let's make it like a vacuum cleaner. Say you're vacuuming your house, your apartment, your room, whatever. That, it's not going to be a set value. Different vacuum cleaners have different intensity values. But a value that would be perhaps appropriate. I don't know the right word I want right there. Appropriate's not appropriate. But an intensity that could fall in the region of a typical vacuum cleaner would be maybe around 10 to the negative 4 watts per meter squared. And again, not all vacuum cleaners would be this intensity, but that would be a general range. If we get up to, say, a loud concert where we're not too far from the speakers, we could get up to approximately 1 watt per meter squared. And there's sounds that are even more intense than that. So there's a huge range of intensity values. We're starting at the smallest intensity of 10 to the negative 12, going upwards to beyond 1 watt per meter squared. That's a huge range of numbers. And so to kind of decrease this scale, this sound intensity level is a logarithmic scale. So we're shrinking, and it's, sorry, before I say that, log base 10 specifically, we're taking this huge range of intensity levels and putting them on this logarithmic scale, which then makes it a much smaller range. So sound intensity level, sound intensity level, we use the symbol beta, so the Greek letter beta, to represent that. We can convert an intensity to decibels using this relationship. So 10 decibels times, this is log base 10, not natural log, so log base 10. I in the numerator is the intensity of the sound you're listening to. So it could be the vacuum cleaner, for example. It could be the speakers at a concert. So it could be anything. So I in the numerator in watts per meter squared, that's the intensity of the sound you're listening to. So that's directly related to the actual energy of the wave, how fast that energy is transferring from one form to another, and how that energy, how the wave itself is spreading over the area it covers. I naught is this threshold of hearing. So in the denominator, we always put the 10 to the negative 12. So let's take this value right here that I estimated for our vacuum cleaner. We can find the sound intensity level by plugging in that 10 to the negative 4 watts per meter squared threshold of hearing is always the 10 to the negative 12. So those units cancel. So 10 to the negative 4 divided by 10 to the negative 12. Log base 10 of that times 10 would be 80 decibels. If we were to plug in this I naught, this would be a sound intensity level of 0. If we plugged in, so this one ends up being the 80, we just calculated that. If we plugged in 1, so 1 as our intensity, we get 120. So now we're going from a scale that spanned 10 to the negative 12 to well beyond 1, to a scale from 0 to 120 and beyond as well. So it's a logarithmic scale though, so we can't simply add decibel levels together. Let's say I was vacuuming. Okay, this is going to be really silly. Vacuuming at a concert. Okay, so yes, that's really dumb. But because these values are on my screen already, is why I'm mentioning that. If I wanted to know the intensity level of vacuuming at this concert, I cannot add the 80 decibels for the vacuum to the 120 decibels for the concert. This is not valid. And that's because this is a logarithmic scale. We would need to add the intensity from the vacuum in watts per meter squared to the intensity of the concert, the speakers, to get a total intensity. And then, once we have this total intensity, we would come up to our equation and find this sound intensity level. So I'm going to put this I total in for I right here. So 1 plus 10 to the negative 4. Divide that by the 10 to the negative 12. Take the log of it, log base 10 of it, multiply by 10, and this still gives us 120 decibels, which hopefully isn't terribly surprising. The intensity, the loudness of a speaker at a concert is going to totally drown out a vacuum. Not that you will ever have a reason to take a vacuum cleaner to a concert, at least not during the concert itself. So we'll go through some examples, both of looking at just intensity itself as power over area, but also sound intensity level, where we're talking about this decibel scale, this logarithmic scale.